Hello everyone, this is Elijah Craig with the Physics 2212 Lab 3 magnetic field of a dipole magnet. The purpose of this lab was to measure the distance dependence of a magnetic field due to a small bar magnet, and then compare those measurements to the distance dependence predicted for on and off axis magnetic fields derived from the Biot-Savart law. For this, we needed a bar magnet, a smartphone with the magnetometer sensor, a meter stick, and some tape. Here are the general concepts we need to know about for this lab. The first one being the distance dependence equation for a magnetic field of a bar magnet, and the second being the Biot-Savart law for a magnetic field caused by a dipole with a dipole moment and observation location. The first part of this lab was to find where the magnetometer was located on the smartphone. Once you had done that, we had to orient the phone along the Earth's north and south axis so that B in the x direction would be close to 0 without the presence of a magnet. And then we had to measure the distance between the magnet and where the magnetometer was located on the smartphone to achieve a B of x, or magnetic field in the x direction, of 20 microteslas, followed by 70, 120, 170, and 220. Once we had all those numbers, we would plot the ln, or the natural log, of the magnetic field in the x direction against the natural log of the distance r between the magnet and where the magnetometer is located, and take the linear regression equation, which is of the form y equals mx plus b. And specifically from this, we need the b value, which is negative 13.408 for our experiment. And then we did similar measurements to find the perpendicular distance dependence. And so we found the distance d perp needed along the x-axis for the B net, or the net magnetic field, to be 100 microteslas. And then, keeping the magnet in the same place, we moved the phone up in the same orientation along the y-axis a distance of d perp and took the measurements of the net magnetic field. And since the Earth has a magnetic field acting in the general y direction, we could subtract the y-axis magnetic field of the Earth from our gathered By value. So this is the data that we gathered from the perpendicular axis equations, and you'll notice that the magnetic field in the z direction for this is 0, because we can ignore Earth's magnetic field, and with the orientation of the magnet and the magnetometer, there is no z-axis magnetic field created from the magnet, so we can just ignore all the numbers that appear there. Here's our calculation for the magnetic dipole moment of the bar magnet, mu. Here we took the distance dependence equation, k times r to the n, and the magnetic field for a dipole, and put them together, or use different pieces of them, along with the value we got earlier, negative 13.408, to calculate a mu, or dipole moment, of 7.515. For this, we also did a computational model based solely on the Biot-Savart law and the previously calculated mu. The magnetic field of a dipole is calculated using this formula that we showed earlier, and this is kind of the general code for that equation, where we created a function that takes in a mu and a distance, or a dipole moment and a distance, and then we found an r hat and an r mag, or the direction of between the distance and observation location and the magnitude of that vector. And then we just basically plugged in this formula, mu naught over 4 pi times 1 over r cubed times 3 times mu with the dot product of r hat times r hat minus mu. Here we have a visualization of the computational model. The orange arrows here represent magnetic field vectors for on-axis fields. The cyan arrows represent magnetic field vectors for perpendicular fields, and the one magenta arrow is the field 45 degrees from the axis. Some general conclusions for this. We noticed that when the magnetometer was farther away from the magnet, it measured a near zero magnetic field in the x direction, versus when it was closer to the magnet, it measured an x direction component of the magnetic field increased drastically. We also noticed the computational B net was larger than the observed B net, and this is likely due to unknown magnetic fields nearby, as this lab was completed in the front yard in a major city. Also, we know if we had set the magnetometer so that Vx wasn't 0 initially, the final values would have been very similar, but the math needed to get there would have been much more complicated. And if two magnets were stuck together, the same test ran on the pair, the values calculated would increase by likely a factor of 2.